So we're going to pick up where we left off last time. Actually, we're going to do a little bit of review just because we were so rushed at the end. But we had these three plans for a query. Select star from T1, T2. So this is easy syntax. We're not doing any natural joins because that's just annoying to deal with the project. So we'll just look at a simple version. And we had a join conjunct in here. I hope everybody's familiar with these terms, conjuncts and disjuncts. So when you have a conjunctive selection, we have multiple conditions ANDed together. So it's conjunctive selection. Those are called conjuncts. If we had a bunch of things ORed together, that would be called disjunctive selection, and the components are called disjuncts. And it's just an easy way of referring to it because you can see that we can move these conditions around in the plan hierarchy, and it has different effects. We don't know all the details yet of the effects, but we're going to start talking about that today. And we pose these questions: which plan is best, and how do we know the plans are actually equivalent? And we'll talk about them in this order. We'll start with how do we know which plan is best? And the way that we talk about this is called costing. It's a simple way. There's other ways as well. We could use heuristics. We could use heuristics to say this plan is preferable to some other plan. For example, we might have a heuristic that we want to perform selections as early as possible, in which case the right plan would be the most preferable, the middle plan would be second most no, that wouldn't be good at all. So basically the rightmost plan would be the most desirable if we said we want to perform selections as early as possible. And hopefully you're starting to get a sense that, well, that heuristic probably works 80 to 90% of the time, but if I have an index on T2.A, my heuristic might actually shoot me in the foot. So I have situations like that can get me into trouble. But right now we're talking about costing, or coming up with a way of estimating the actual effort required by the plan. So these are the most basic measurements, and these are the ones you'll have to add to NanoDB. I believe that this is all we really require in NanoDB. Number of rows generated by each plan node. So how many rows does the T1 can generate? How many rows does the T2 can generate? And so forth. And the number of disk accesses that have to be performed by each plan node. And then, of course, you can start getting into more advanced things. How much memory do I require? What's my minimum bound? And how much would I like to have? And that obviously becomes very important when you start having concurrent query evaluation, as we talked about last time, because things like sort, merge, join require additional buffer space to be useful. And hash joins, hybrid hash joins in particular, require extra memory to make sure that they're evaluated efficiently. So sometimes we have those kinds of measures as well, and we won't think about that in too much detail, although we'll talk about it a little bit. But here was the example that we had. Select b greater than 5 on T2. And so the question was, the two questions we asked, how many disk blocks are accessed? And hopefully everybody sees that we have to access all the disk blocks because we have an assumption about the storage format of T2 right now, that it is a heap file. Like if we had a sequential file, maybe we could come up with a better way of evaluating this query, b greater than 5, by looking in the file somehow and finding where the values start with 5 and then go from there. But since it's a heap file, we have to look at everything. How many rows will be produced? And this is where we kind of ran into a brick wall. So we had this assumption, and this is what we will again be doing in NanoDB. It's a very basic approach. Most databases are much more sophisticated than this because this is so basic that it doesn't really help you a lot when you get into sort of common working data sets that people end up working with. We'd like to have a much better sense of what our data actually contains than just the minimum and maximum values. So we have a huge assumption. B is uniformly distributed. And we make a guess that since we want to find all the stuff where B is larger than 5, well, we'll just say, I'll figure out what this how would I describe this? This fraction is, this ratio. The maximum value of b minus my lower bound 5 over b max minus b min. Assuming uniform distribution, obviously this is not going to be a whole number, and it's a bad idea in general to keep track of your number of rows in your costing as a whole number because it very quickly becomes a fraction, and you would like to keep the fractional component so that you have some kind of slightly useful answers. But hopefully this also illustrates how you could tell the answer to this much more easily with a histogram. CS123 projects, it's funny, but a lot of people have added histograms to NanoDB over time. That seems to be a very popular CS123 project to do. And it's pretty straightforward to do, actually. There's a few decisions you have to make about how you generate these histograms, but in general, it's a pretty good project, pretty straightforward. Certainly something that one person could do by themselves. So these were the things that we talked about. Our ideal goal with plan costing is that we have estimates that are pretty accurate. Like if I said, here's my estimate, I'm going to read 250 disk blocks. I run the query and it reads like 248 because I'm just so awesome. But that's not really realistic. Okay? But anyway, like I say, your estimates should be easy to compute. They should be logically consistent. So for example, we had these 3 versions of select star from T1, T2. It would be really neat if at the top plan node, our cost estimate had about the same number of rows for each one of these plans. Because they're all supposed to be equivalent, they should all produce the same number of rows. You could imagine that other places inside this plan, you might have very different number of disk blocks generated, very different number of rows generated. For example, our leftmost plan with a cross join, basically, between T1 and T2, that's going to generate all the rows. And hopefully our selection will limit it down and we could use our estimates to figure that stuff out. But you can see how this, there's certain things that will vary, but there's certain things you would like to be the same with these different plans. We'll see if they actually turn out that way. The reality, though, like I said before, is that even though these are our goals, they're very difficult to achieve. And so what we generally require is that the fast plans have the lowest cost. We don't really care anything beyond that. We don't even care about the units. Disk block reads. Typically what you see in database planners is when you do an explain plan and it has costing figures associated with it, it's just some number. And if you look at Oracle's explain output, for example, it has numbers associated with each plan node, and if it's a big number, it's bad, and if it's a small number, it's good. And that's really all that you get as far as the planner optimizer. And so we just really need that our planner optimizer generates large costs for slow plans and small costs for fast plans. So, and NanoDB will do this, and it's funny because when you get to like assignment 4, you'll build a planner that takes advantage of this stuff to generate optimal plans, optimal in air quotes, of course, and it does a pretty good job. It's actually kind of neat that it's able to come up with pretty decent plans. If you throw it various queries, it will figure out where predicates should go to try to optimally execute the plan. Now, if we're going to make costing estimates, if we're going to estimate how many tuples are output by a particular plan node, it's clear that we need to have some kind of statistics for our data. And we already saw a basic idea of, well, if I keep the minimum and maximum for each value, I can use that to guesstimate how many rows a particular selection predicate will select. So like I say, the statistics are generally expensive to compute, and this is part of the reason why on the first assignment, we don't want you using stats to figure out how to optimize inserts. Now, I don't mind if you statically use stats. Like I'm going to use the guess of the row size as a statistic for figuring out what, like I was saying, the average row size would be a great way of telling when is a page full or when is it non-full. That would be kind of helpful to know the average tuple size and maybe also the minimum and maximum tuple size. But computing that requires scanning over the entire table, and that's slow. We don't want to update it incrementally because that's going to generate a lot of I/O. So in general, databases don't. But yeah, like I say, the statistics don't need to be perfect. They just need to mirror the data reasonably well. And you'll notice that some of our statistics that we keep track of, the number of distinct values in a column, the min and max values in a column, I suppose you could come up with ways of updating some of those things in some situations. But if you have insert selects or updates going on, it may be much more difficult to modify those things. So as long as the statistics are reasonably close to the actual data, we don't mind. That's fine enough. And yeah, like I say here, if the statistics are very different, then we'll have problems. Basically, databases have this command. I'm going to mention it in a future slide. Typically analyze or analyze table. I think that Postgres is called vacuum analyze. And you give it a table name or you give it a sequence of table names. And what it does is it locks the table so nobody's allowed to change it. And then it scans through the entire table computing statistics. And then it saves those away and then unlocks the table so that queries can then operate again. So then you know that the statistics are up to date, at least at that point in time. So here's some useful statistics. Obvious ones. Number of rows in the table. That should be a really obvious one. The number of blocks containing tuples. Now, in our heap files, remember that we basically had a simple format where we didn't have empty pages. I don't know, did anybody introduce the concept of a completely empty page in your heap file changes? So that's something that can be useful. Like when a page becomes completely empty, then you can mark it as empty, and then that might allow you to relocate or reclaim pages in your heap file so that they can shrink as well. Most people don't do that because it's not generally required by our testing or the assignment. So that's probably good because it would be too complicated otherwise. But anyway, and so in our heap files, the number of blocks containing tuples is basically going to be the number of blocks in the file minus 1 for the schema block. But you can see that for other kinds of files, in fact, when we start talking about B trees, it's very common to have empty blocks because B trees, the files can grow and shrink, and it's nice to know what blocks are empty so that we can reuse them when we need a new block. Average size of a tuple in R in bytes, so that's another thing that we could keep track of. The blocking factor of a table. So this is a derived value, or I should say you can derive it from these other things. Like I say here, the blocking factor is just going to be, the number of tuples divided by the number of blocks containing tuples. So it would be n sub r divided by b sub r. So that's not very complicated. And of course, you can do the math. It's really easy to see that this relation is generally going to be true as well. The b sub r is going to be n sub r over f sub r. Very exciting, right? So anyway, there's not a lot of... The reason why the average size of a tuple in R might be useful, again, is if you're doing a distributed database, or you want to see what joins are going to produce, or if you need to estimate the buffer space requirements of a particular plan node's output, like if you're trying to reserve space for a sort merge join or something like that. See, other statistics that are very useful. The number of distinct values of an attribute in a particular table. We're going to be beating this one to death. You'll be surprised at how much we actually try to squeeze out of these statistics. It kind of makes me feel dirty every time I see it, but it actually works pretty well. So number of distinct values. Notice that this is some kind of mapping. So we say number of distinct values for a particular attribute on this table. That's the A, and then R is the table. Minimum value for an attribute A on a table R, and the maximum value of an attribute A on table R. So these statistics turn out to be very helpful for figuring out how many tuples are going to be generated out of a particular plan. And then, yeah, here's where I talk about the analyze. NanoDB has an analyze. I can't remember if it's analyze table or just analyze, but it can take a sequence of table names, so it'll just run the analysis phase on all the tables. Except that it doesn't yet because you have to implement statistics collection. Whoa, well that's hard. I mean, you basically just scan through the table block by block and update your stats. It's, all the other machinery is actually given to you for updating stats, and you just have to traverse the file and generate the stats. So it's pretty straightforward. That'll be on the third assignment. Selection. Okay, so we have this select plan node with some predicate theta, which may be true if we don't have any predicate, on some table. And so we're going to estimate the number of rows produced with this simple expression. You can see the number of rows times this probability that the predicate will select a given row. And that is going to be our estimate for the number of rows that the select produces. We call this estimate the selectivity of the predicate. So how much does it select or how little does it select? And you can see that this probability is going to range between 0 and 1. So for example, if we had really good statistics and we knew that the value being selected doesn't appear anywhere in the table, the selectivity would be 0. And we'd know that the plan node produces nothing. If we said, I want to select tuples with the value in this range, and we know the range encloses the min and max value, we would estimate the selectivity at 1. So we can use this as an estimate. So this is kind of nice because now we've turned this into a problem that's a little bit more general. We just need to figure out selectivities of predicates, and if we figure that out, then we can apply this both to selects and also to joints and anything else that needs predicates. So like I say here, assume that R is a heap file, so that the select is basically always going to read all the blocks in R. And as I said before, if you have different file organization, that may change that markedly, but we won't talk about that right now. You obviously would need to have code specific to specific kinds of table files or tuple files to compute these selectivities correctly. Okay, if you have the attribute being compared to some constant, very common in predicates to have some attribute being compared to a constant. And as I say here, without a histogram, we have to use a really hand-wavy answer. We use the minimum and maximum. If the value is less than the minimum for that column, we estimate the selectivity as being 0. Hopefully that's obvious. Now, is this statistic correct? Maybe. It depends on if we ran analyze recently. And so this also gives you a sense of why having out-of-date statistics could have such a profound impact. Because we may have a plan node and estimate a very low selectivity for the plan node, and in fact the statistics are out of date and the selectivity is much higher, and we end up selecting a plan that does a whole bunch of extra work that we didn't know we'd have to do. So you have situations like this. If V is greater than the max of attribute A's value in table R. So notice I'm doing predicate attribute is less than or equal to some value. If the value is beyond the maximum, then I estimate the selectivity as being 1. Now, if it's in between, then I do that crazy calculation that I had before. Now, I'm seeing if the attribute is less than or equal to some value, so I basically start at the minimum and then go to V, and whatever extent that is, that basically corresponds to my selectivity. So V minus the minimum of that attribute's value over the maximum of that attribute's value minus the minimum of that attribute's value. Okay? Does it make sense? Can you do this for ints? You can do this for ints. Can you do this for strings? It's not really generally useful, but we use it wherever we can. Okay? So you'll notice this, again, when you work on the selectivity estimates in assignment 3. The selectivity estimator has a set of types for which you can do this kind of computation. And so you can just use it in those situations. I can't remember if it does it for you or if it just tells you how to do it or what. But generally, you don't have to worry about that kind of thing too much. It also does this calculation for whatever type it's passed. So because doing this for ints and then also for floats and also for doubles and also for longs and also for bytes gets annoying. So I just give you some code that does everything through the expression system so that you can compute this value easily. Now, if you want to see if an attribute is greater than or equal to some value, what's the selectivity of that predicate? Basically, all you're doing, can anybody tell me the one change that you make to your estimate? Well, but I'm doing a calculation. So the selectivity of attribute less than or equal to value equals this expression. So how would I change the expression for attribute greater than or equal to value? Really simple. I change it, yes. V minus min to what? Somebody tell me what I change it to. Yeah, so it's just max minus V. Super simple. Okay. What about attribute equals value? Well, we don't use min and max for this. What we do, I mean, you could actually. You could say if this is less than, V is less than the min or it's greater than the max, the selectivity is 0. Because you're assuming that the value falls outside the range you think the value can take. So assume uniform distribution again. And so we're going to estimate, presuming that it falls within the range, that the selectivity of an equality comparison is just going to be 1 over the number of distinct values of that attribute. Yay, aren't we cool? So we're just going to make that assumption. So the number of rows, like I have here, is the number of rows input, so whatever r's total number of rows is, divided by the number of distinct values of that attribute that I'm doing the equality comparison on. Uniform distribution, yay, yes. NanoDB keeps all of its statistics for a given table after the schema for that table. So again, it's going to be in block 0. If you look in, what is it, heap tuple file manager, please forgive me, this is Java's curse of long class names. But if you look in that class and create table, you'll see that basically it uses a schema writer to write out the schema, and then shockingly it uses a stats writer to store the stats immediately after. Except that right now the stats are basically empty, so it stores dummy stats. So that's one thing you'll have to update for assignment 3, but not this assignment. Block and page, yeah. So and when I say block in lecture, I mean a DB page. Yeah. And if I say the schema block or the header block, I mean DB page 0. All right, yes. Any other questions? Okie dokie. So, yes. What if A is a primary key for R? What can I estimate my number of rows will be? Again, presuming that it falls within the min and max of this. Yeah, 1 would be good. Now, does our math work out so that it would be 1? It's kind of cool. It does. So that's a nice vote. Okay. The number of distinct values of that attribute A in R is going to be the same number as the number of tuples in R. So given that that's the case, if we plug that in, then we end up with 1. So that's pretty nice. Okay. Now you don't want to jump through all the hoops if you know it's a primary key, because there's other things you can optimize as well, but at least the math works out. Okay, now yeah, and I mentioned this note before, I'll just touch on it again, that if we have a file scan and we happen to be applying a predicate that involves all the primary key attributes for the table, then guess what? We can stop after we find our first tuple. And so that will greatly reduce our average case block reads if we have a large file. Obviously, if it's a tiny file, it won't affect it as much. Okay? But it's still good. So anyway, that's just a little note. We already talked about that. Of course, you can also have the inverse of these. We talked about greater than or equal, less than or equal, and equal. So all these things involve equality of some kind. So if we want to do just a greater than or less than or not equals, we basically just say, well, that's 1 minus the corresponding, or I should say the complement of the selectivity that we're looking at. So attribute greater than some value would be 1 minus the selectivity of attribute less than or equal to the value. And if you have not equals, then that's just 1 minus the selectivity of an equality. So that's pretty straightforward. Same thing with negation. And again, you can do all of this in the selectivity estimator. If you look at that code, if you're really curious, you can look at that code, and you'll see that there's cases for all of these things, and it's pretty straightforward to plug in. Complex selects. If we have multiple conditions, remember we already made this crazy assumption that our data is distributed uniformly, so we might as well make some more crazy assumptions. We're going to assume that the conditions are independent of each other. So if we have all these conjuncts, we'll just compute the selectivity of each conjunct and then multiply them all together. This generally is a safe assumption. One of the assumptions that shows up badly in NanoDB right now, and you'll probably notice this in assignment 3, and it's a nice thing to fix, is that if you say select star where A greater than 5 and A greater than 5, it miscalculates the selectivity of that expression because it thinks those are independent of each other. And that's not really a good thing to assume. You could probably imagine other situations along those lines where you could run into trouble. So, intelligent databases will do some analysis to see, well, are these conjuncts actually related to each other in any particular way that I need to know about? But we can do the very simple thing and just ignore that problem for now. Disjunctive selections, well, this is a little bit more complicated because how do I know what the probability of theta 1 or theta 2 or theta 3 selecting rows, how would I figure that out? Well, the easy approach is just to say, well, I think I have this written down. If I have this selectivity of theta 1 or theta 2 or so forth, is the probability that a tuple satisfies at least one condition. So that's just 1 minus the probability that the tuple satisfies none of the conditions. And that's pretty easy to compute. There's a lot of 1 minuses that start showing up. But you can do this kind of thing relatively easily. Disjunctive selection will be another thing you add to NanoDBs, although I don't have any tests for it. So you probably be on your own for exercising that. But you could exercise that relatively easily. Okay? All right. Let's see. Yeah, so this is an issue that I have written here. Conditions are only involving attributes and values. Has that bothered anybody yet? I mean, it's kind of nice. It's a safe assumption. It's kind of cool. But this is not reality. And I have a few examples here. I think we had something like this in the first assignment. Select star from employees where salary times 1.05 is greater than 100,000. Because we wanted to give a certain raise to some people as long as their resulting salary wouldn't be 6 figures, because we want to hold them down. And then we give a different raise to people with a salary if the result would be over 100,000. So that's one example. Now, in an intelligent database, you could probably all reason about this. An intelligent database could figure out what salary would be compared to in the situation and then estimate things properly. But what if you have some kind of opaque function, some black box that you're trying to use? In this situation, we decided that we want to get rid of all the unpopular employees. So we have some metric by which we measure popularity. Maybe their Facebook social graph or something like that. We use that to estimate how popular they are, and we axe everybody who sucks. How do we estimate the selectivity in this situation? Anybody have an idea? Well, what have we been doing so far? We've been guessing a lot. So why don't we just keep guessing? We just say, well, I have a conjunct, I have no idea how to figure out a selectivity, so I'm just going to say, by default, the selectivity is going to be some constant. And so like it says here, you would have 1/2 as an example when you expect that this is going to be a common situation, so it will probably select more than a few rows. And you might estimate something a little bit more stringent if you expect it to be uncommon. Now what's interesting about this is it typically when people are issuing queries and they're specifying predicates, they expect to actually get a small fraction of the rows. If you look at general database usage, if they're not specifying predicates on a particular table, they want to consider all the rows. But if they do specify predicates, they want to see a relatively small number of rows. So just guessing the selectivity as being small is a pretty good way of approaching things. A lot of databases do this. NanoDB has a pretty broad estimate of 25% in these situations, which is, I don't remember what Postgres's was. I vaguely recall it's like 10%, but you can make small estimates like that when you have situations and you can't estimate them any other way. Yeah, question?
About simplifying the strategy.
Mm-hmm.
Like in salary times 1.5, you can just divide 100,000 by that.
Yeah, you could do some. Yeah, you could divide both sides by 1.05 and then. Yeah, so you could basically implement the smallest possible part of Mathematica that one could implement and see if you can simplify these expressions. Yeah, definitely. I don't know if any of you have noticed, but in the expression support that NanoDB has, it has some very basic simplification capabilities. There's this notion of normalizing an expression, which basically makes sure that when you're comparing two columns, the column that's lexicographically first is always on the left, so that it becomes easy to figure out if two columns are participating in multiple selections, or if two expressions are the same, or so forth. So it'll always try to make sure that the column expression is on the left and the constant is on the right, and so forth. So it tries to do some simplification. It tries to collapse arithmetic operations and so forth. But there's only so much that NanoDB tries to do. So it certainly wouldn't be able to do this. Yeah, question? Yeah, I mean, it's kind of an interesting thing. It's a good question. Should we retain statistics of earlier evaluations? You could, especially in the situation with functions. If you had functions that were used pretty frequently, then you could keep some kind of memoized details about, how selective they were, or something like that. Um, I kind of like that idea. I don't know that many databases do it. You would just have to make sure that you had some kind of way of keeping that information from growing unboundedly. For example, in this example, delete from employees, if you were doing this at Walmart, I don't know, I don't think Walmart does that, but they have a lot of employees. And so if you're running this kind of predicate, or this kind of predicate, you would have to be very careful because you couldn't just keep track of compute popularity for each employee ID. But maybe what you do is you say, I'm keeping track of compute popularity of employee IDs and the selectivity of that particular conjunct. Maybe you could do something like that and actually see what it produces. That would be an interesting thing to explore in a 123 project, but it would probably also be challenging. But that would be fun. Okay? Any other questions? Okay, so these are some details of how we guesstimate in the situations that are too hard to estimate. Now, also, like I say here, these were all against a table, and we generally have statistics for a table. NanoDB is written so that we can do this without statistics because we don't have statistics for like the first half of the assignments. But we frequently have situations where we have subplans, and we need to figure out statistics so that we can estimate things above the subplans as well. So we need to figure out what the plan nodes produce as well as what they consume. And the number of distinct values and the minimum and maximum values generally are the hardest things to estimate. Some of you have already seen this in plan notes. Oh, Donnie has a to-do in there saying these statistics for the plan node output are hard to compute. Do it later, or do it never, or something like that. I can't remember exactly what it says. But that's the reason why, because estimating these things tends to be quite hard. You can do it in a lot of situations, but it's a bunch of grungy bookkeeping, and that's not exciting to me, so I didn't write that. If that kind of stuff is not grungy and not boring to you, then maybe that's something you could do for a future project. The selection involves inequality. Well, like it says here, we can say that the number of distinct values for that attribute is now 1, because we know that we selected for one value of that attribute, and we also know the minimum and maximum of that value. All the other attribute values we could basically leave unchanged, because again, we're assuming that the column's values are not correlated in any way. Okay, so we have a lot of assumptions, but this certainly would work. And you can use this pretty effectively because a lot of selections are retrieving rows based on some key. And so you can actually do these estimates quite easily. If we have a comparison, then we can just use our value to figure out what the new min and max are. And like I say here, we're assuming that the minimum and the maximum enclose the value that's used. If it doesn't, then our min and max become unnecessary because our number of rows output becomes, the estimate becomes 0. But in the situation where we actually expect to generate some non-zero amount of rows, we can just update our minimum and maximum appropriately. Okay. Yeah, and so we do, again, this fun computation to figure out the estimate for the number of distinct values. You can see why I'm not interested in adding this stuff, because it's like, oh, that's so boring and tedious. So yeah, this is the easy computation to do, and this is why selectivity is so helpful, because you can see that our number of distinct values has the same expression that our selectivity computation had. V minus the minimum value over maximum minus minimum. So we can use that to constrain our number of distinct values estimate as well. We just take the input number of distinct values and multiply it by the selectivity. Okay? So that's pretty easy. And it's kind of close to right, maybe. If we have a situation where our predicate is expected to impose a certain constraint on the values that the value can take on, we have an in clause. Remember that we can have in clauses that are not scalar subquery, or not scalars, just flat subqueries. We can have a list of values, a list of literal values that we specify in our in clause as well. Then, in this situation, we could actually constrain colors. I mean, min and max we could do for strings, but obviously we don't, and we could also compute the number of distinct values, but we don't use that in comparison estimates. So we just have the number of distinct values being the number of values in the predicate, or maybe we want to be more sophisticated and say the number of distinct values in the predicate, and we can compute the minimum and maximum as well. In this situation, orange would be the minimum and yellow would be the max. Okay? So, and if you have another situation, what do you do? Well, what we do here is we just figure out how many rows do we expect to be output. We'll just assume the worst case and assume that the number of distinct values can be no more than the number of rows being produced. And so we can just pick the smaller of either the input's number of distinct values or the number of rows we expect to output. That's going to be an upper bound on the number of distinct values. Clearly, if I only output 10 rows and I have 100 distinct input values, I'm only going to have 10 distinct values output at a max. Okay? So what do we do with min and max? I don't know if I talk about it. I don't know if I want to talk about it. Yeah, I don't talk about it. Yay! Okay, any questions about those so far? Because that's selection. That's the easy part. Now we're going to start talking about joins. We need to think about number of rows produced, which is pretty easy, except when it's not, and the number of disk IOs, which we already talked about. And it's interesting because the second value, like I say here, is harder to estimate, mainly because we don't know how much the buffer manager will help us. And this is where being able to reserve resources, particularly buffer memory resources, with the buffer manager would make it very helpful to be able to figure out how many IOs are expected in this particular situation. Most of our, our costing estimates of the number of seeks and the number of disk reads, or disk reads and writes, if you're doing something like a hash join where you have to partition the data, we need to know how much space we have in memory to cache data. And so we just kind of hand wave on that one. Typically what I have you do in NanoDB is just pick the average case, or the best case, because, well, you guys have all seen, managing buffer space is a little bit tricky, and so we just assume that we're going to have enough buffer space. Because we don't have concurrent usage, and we may not until the very last assignment if we do it all. So the disk IO estimate, it's approximate, and ideally the estimate that we use based on the join algorithm we're using will give us results that actually correspond to the amount of work that actually ends up being done. Okay, so we're not really going to talk too much more about disk IOs because we already kind of covered that in pretty good detail. So we're going to focus on the number of rows produced. If it's a cross product, yay! Easy time, right? Total number of rows will be the number of rows in the left table times the number of rows in the right table. The average tuple length is also easy to compute. And if you think about it, selection, the average tuple length doesn't change. I suppose it could change, but we don't change our estimate of the average. And so in this situation, though, it does change. The average tuple length is just the sum of the input tuple lengths. Input average tuple lengths. Theta join. Well, we can think of this as a cross join that's followed by a selection. But now we have an interesting challenge, right? Are we comparing columns to values anymore? No, we're comparing columns to columns. And so we have to figure out how do we estimate the selectivity of comparing two columns to each other. Typically, it's an equality comparison. I don't think we actually talk about inequality comparisons, but we only talk about equality comparisons. So this is where it gets tricky. Let's look at this specific theta join. R theta join S on attribute A. So R has an attribute A, S has an attribute A, and we have statistics for these things. So we know the minimum value and the maximum value. Maybe what we could do is do some special checks to say, well, R's min and max on A doesn't overlap S's min and max on A. Estimate is 0 rows. We're done. Dust off the hands and move on. So we could do something like that. Generally, that's not going to be the case, especially if we actually have referential integrity here. So we have to go ahead and look at these things. If r.a is a key for r, what's the maximum number of rows that this theta join will produce? I'm sorry? The minimum of r.a and s.a. We can constrain this better than that. That's a good start. I'm sorry? Yeah, it actually turns out to be the number of rows in S. Because we know that each row in R is going to join with 0 to n matching rows in S. But the rows in R are not going to multiply because each one only appears once. So S's number of rows turns out to be the factor. Okay? This is a very common situation. So this is a great estimate. And guess what? It's super fast, too. Now, if S.A is a key for S, we have a similar situation. We can just estimate the number of rows produced will be the number of rows in R. Okay? So this is nice. Now, of course, then we have the situation. Well, actually, this is another special case. So what about this one? Both are keys for their respective tables. So every tuple in R is going to join with 0, 1 tuple in S, and every tuple in S is going to join with 0, 1 tuple in R. So what's going to be the estimate? Number of rows. Yeah, it's going to be the minimum of the two tables' number of rows. Now, obviously, this is theta. This is inner join. Outer join, the estimates will be a little bit different. But this is very common. I mean, we've all written A natural join B, natural join C, natural join D, or A join B using blah, 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 and so forth. So we have a lot of situations where we have inner joins, and at least one side is a key, so we can do these estimates. We can do them very fast, and they're useful. They're helpful. Now, let's say that neither r.a nor s.a is a key. This is bad schema design, but we will ignore that problem because databases have to execute bad SQL on bad schemas as well as good SQL on good schemas. So again, we make this assumption that A is uniformly distributed. And we come up with an interesting situation. We can look at it from the perspective of a tuple in R. How many tuples in S could that particular tuple in R join with? And you can see that we just say, well, how many distinct values for that attribute in S are there? That becomes our selectivity for that tuple. And so we estimate that it will join with the number of tuples in S divided by the number of distinct values of that attribute in S. So we're looking at it from R's perspective. I'm sorry? Well, so do you have easy access to this? In NanoDB, the statistics keep track of the number of distinct values for each attribute. The problem is, how do you compute that? Yeah, I mean, well, so it's easy to compute it. I mean, I think all of you would know exactly how to do it. I keep a hash set in memory, and I add values as I read them out of the table, and at the end, the set size is the number of distinct values in that attribute. Well, what if that table is like a terabyte, and the number of distinct values, you know, let's say that it's a key or something. Well, actually, yeah. So you still have a problem because keeping all the distinct values in memory can become prohibitive. So you have to think about those kinds of situations if you want to do these stats computations generally. But we pretend we live in this lovely world of make-believe where everything fits in memory in NanoDB. So you can just scan it. And again, this is what you'll have to do. The stats collection mechanism has a lot of these tools in there already for you, and then that gets stored into the table's stats, and so you can just look it up very easily. Was there a question?
Yeah, so it seems like blue
They may be, but I don't know anything about bloom filters, except that it's a thing. Yeah. So that would be another really cool thing to explore, and how you could apply something like bloom filters to this. I wish I knew more about that. I've spent a little bit of time reading on those, but not enough to have retained anything, unfortunately, at this point. So anyway, yeah, so that would be another cool thing to explore. I'll add that to the list. Let's see. So yeah, so this is the suggested estimate. If we look at this from R's perspective, tuples and R's perspective, that the theta join of R and S is going to produce the number of rows in R times, so we've already estimated the number of rows that a single tuple would join with, so we just multiply that by the number of rows in R. And R times NS divided by the number of distinct values of A and S. And then we could do the same exercise standing on a tuple in S. So we could do the same estimate in reverse. And you go through the same reasoning process and you end up with NS times NR over the number of distinct values of A and R. So it's kind of weird because now we have two answers. And we have to figure out which answer we like the best. Well, I'll tell you in general, we like the answer that gives us the smallest number because that means it's the lowest cost. But we have to come up with some rationale, so we can just wave our hands a little bit more. Okay, we have these two estimates that we computed. The NR times NS over the number of distinct values of A and S, and NS times NR over the number of distinct values of A and R. What we can do is we can look at the number of distinct values there are of this join attribute. Okay, like I say here, the number of distinct values of A and R as compared to the number of distinct values of A and S. If we have fewer distinct values in R, what does that kind of tell us about who's going to govern the join more? Who's going to restrict the number of rows in the theta join more of R and S? R's got fewer distinct values, so it's a reasonable guess that R is going to constrain the output more than S will. It's a guess. Okay. And you could do the same guess if the number of distinct values in R is greater than the number of distinct values in S. So like I say here, we expect that more tuples in S will not join with any tuple in R. So we go ahead and use our estimate based on the perspective of tuples in R, which turns out to be the nicer one in this situation. Okay. So we divide by the number of distinct values in S, and that makes us happy because our estimate is lower. And we can do the corresponding guesstimate if we say the number of distinct values in R is larger than the number of distinct values in S. We just assume that, well, more tuples in R are going to be left out. S is going to be the governing thing, so we use the second estimate. So we end up with some computation like this. Notice our last line. If we have a theta join between R and S, or let's just constrain ourselves, the theta is just R dot A equals S dot A. In this situation, we just multiply the number of rows in the two inputs, and then we divide that by the larger of the two distinct value statistics. Okay? And that becomes our theta join estimate. All right? Now we have joins in multiple conjuncts. We just jump through the same crazy hoops again. So we can, this is where it becomes important to start looking for keys. And this is something that NanoDB definitely does not do. So this might be a fun, well, actually we don't support keys yet. So it would be fun if we had keys, but we don't have them yet. We haven't gotten to that point in the course. You may have noticed that there is a mechanism for representing keys, but we haven't gotten there yet. So we need to look for keys, though. We have this set of attributes. We need to figure out if there's anything in there that's a key. If there is, then we can use our key estimates, and that makes us happy. Multi-column keys are pretty common, so these kinds of joins are pretty common as well. If we have a set of attributes that's not a key for either side, then we have to do our crazy hand-wavy assumptions. And so we assume these conditions are independent, and we do our computation so forth. Okay. It's really not rocket science. Now, this is the selectivity of the join predicate. That's why you don't see NR and NS in this calculation. This is just the selectivity. So we take that and we multiply it times NR times NS, and that gives us the selectivity of our join predicate. Okay? Is everybody feeling really approximate right now? Because that's basically what we have. Okay, outer joins. I don't like these estimates. You will find them in database texts, but I don't like them because I think you can actually do better than this. But like it says here, we're only using the number of distinct values, not min and max, to further constrain these or refine them, is a good word. So the left outer join, we'll just assume that it's the theta join selectivity or the theta join estimate plus the number of rows on the left side. Why is it so large? I don't know. But that's what they say you should do. That seems awfully high to me. Same thing with right outer join. And same thing with full outer join. Like I said, I really don't like these estimates, but they're fast to compute, and so you can get a pretty good approximation. So if you want to explore this, what I'll probably do in assignment 3 is have an option in the design document for you to explain any deviations that you took from the slide estimates. If you have good rationales behind them, then that'll probably be a nice thing to explore. Okay? Let's see, what else do we have in here? So other plan nodes, project. We'll try to get through these. You know what? It's 5 till, so we should probably stop. We'll go ahead and finish these other plan nodes. We have project, grouping aggregation. Grouping and aggregation, you can actually make some pretty good assumptions about number of distinct values, min and max values, and so forth, because the groups constrained, the group attributes are pretty constrained. So we'll talk about that next time. Are there any questions? Okay, and then we'll get into equivalence as well. So we'll see you on Friday.